I'm Scott. I'll be talking about when your AIs deceive you. It's work done with these wonderful collaborators. This is reinforcement learning from human feedback. It's become a staple fine-tuning technique used in ChatGPT and many other language models. The human is shown two state trajectories produced by the agent. The human gives a preference, in this case that they prefer trajectory S to trajectory S prime. Prior theoretical work shows that with sufficient data, this is guaranteed to be optimal. For anyone who's tried RLHF, you're wondering, guaranteed to be optimal? This is an example of a failure case that was in the blog post accompanying the original deep RLHF paper. The human was giving feedback on this robotic hand through images that they received from a camera. It led to a policy that only appeared to be grasping the ball. This is another failure case that's been hypothesized. It's a thought experiment where an AI is being trained to defend a diamond in a vault. The human gives feedback, again, from a camera image of what's occurring in the vault. The hypothetical failure case here is that if a burglar came and posted a screen in front of the camera as if the diamond were in the vault, then it would appear to the human that the diamond is safe. The key issue, again, is that the human is giving feedback while not seeing everything. You might be wondering, are these hypothetical scenarios, or do we have real-world applications where the humans are giving feedback while not seeing everything? This is the release of the ChatGPT plugins feature. Here, the AI is taking actions, reading web pages, and surfing the web. The human has a thumbs up or thumbs down button while only seeing a summary of the agent's behavior. It can get even more severe. So this is from that same plugins release. In this case, the agent is helping the user by writing code. So the AI has written a bunch of code, and there's just a show work button, but the human doesn't have to click it and can still give the thumbs up or thumbs down, even if they haven't seen any of the things that the agent did to accomplish the task. In fact, if the human were not a programmer, then the show work button would effectively be useless. So we have this challenge where we want to give feedback to agents, even though we can't observe everything they're observing. And in fact, the AI might even have more knowledge than the human. The human might not have the knowledge they need. That's the central question of this work. What happens when humans provide feedback from only partial observations? To formalize, we'll define our setup based on this observation model O. We assume that the agent still observes everything. The agent observes the full state sequence. The human just gets the observations from the model O. This is the standard preference comparisons from regular RLHF. When the human can fully observe the state, the standard model says, this is known as the Boltzmann-rationality model, that the human computes the ground truth return, G, by summing the rewards at each individual state. The higher the reward of a state is, the higher G of S, the higher the probability that the human prefers S to S prime. The equation beta here is just controlling how much or how little noise. This is the inverse of noise in the human probability, and the sigma is giving us a probability distribution. The key thing to know is that the higher G of S is, the higher the probability that the human assigns their preference on S. In our model, because the human can only see observations, we assume that the human forms a belief about the underlying state trajectory. We replace the true return, which the human now doesn't know, with an expectation of the true return according to this belief function. This gives us our model for humans that are making preference comparisons under uncertainty. The key feature is that they're taking an expectation of the return according to their belief. This is the model that underlies all of our results. We assume this human model. So the first question we ask is, if you just apply RLHF naively, you do what you've always been doing without changing the algorithm at all, what happens? So we show that we will denote by g-obs this observation expectation that the human is taking. And we show in the paper a proposition that naive RLHF will learn to rank the policies according to j-obs. So j-obs is g-obs, but averaged over all the states that might be seen in the policy rollout. And yeah, we show that RLHF learns to maximize this observation return. This gives us the question, when j and j-obs are misaligned, so when the human is not perfectly estimating the return, what kinds of policies are optimal to j-obs? These are the types of policies that the agent will learn. I'll start by giving you an example that we use in our paper, and then I'll generalize. So here's the example failure of what happens. The AI terminal assistant is helping the human to install software. The human doesn't see the actions, but only sees the terminal output. In the first case, the AI successfully installs the NVIDIA driver. Then the AI goes to install CUDA on top of the NVIDIA driver, and what happens to the agent is what happens to me whenever I try to install CUDA. An error is thrown. So there's negative reward that the human believes from seeing this error. Now, the agent's going to try a different strategy. So it doesn't know any better. It's going to install NVIDIA like normal, and it's going to also append to the installation command to /dev/null. This is a terminal redirection, which processes the standard output like normal, but simply redirects the standard error into a black hole. The AI learns this is the optimal strategy in this environment. So that's a specific example. Now I'll talk about the general theory that we've developed to help us characterize when this happens. The key idea is that the agent has an incentive to maximize the human's estimate of the return rather than the true return. This leads to two types of opportunities that the agent wants to exploit. It wants to make the human overestimate the return. It also wants to correct the human when the human is underestimating the return. To formalize this, we have two types of errors. We decompose g-obs minus g. That's the difference between the true reward and the human's observation estimate of the reward. We decompose that into its positive and its negative components. The positive components are the overestimation error. The negative components are the underestimation error. It'll be useful to think about the on-policy averages of these two objects. So the objects on top are the state level. We also have the on-policy averages below. So to understand the space of possible behaviors, I'll map it out. So we're mapping overestimation versus underestimation error horizontally here. And we'll think about increases or decreases in these types of errors on the vertical axis. We'll call it misleading when the agent is increasing error and informing when the agent is decreasing error. In terms of misleading the human, if it's increasing the human's overestimation error, we call that inflating. It's when the agent is making the reward seem greater than it actually is. When the agent is increasing the human's underestimation error, we call that downplaying. It's when the agent is making the human believe the reward is less than it actually is. For informing the human, we'll call it disillusioning when the human is decreasing the human's overestimation error. It's making the human realize that the reward is not as good as they thought. We'll call it justifying when the agent is decreasing the human's underestimation error. This is making the human realize that the rewards are better than they thought. Our first theoretical result is that when RLHF is misaligned, it incentivizes the inflating and the justifying behaviors. These are the two types of behaviors that will increase the human's estimate of the reward. We're going to focus on a type of inflating that we call deceptive inflating. It's based on Peter Park et al.'s definition of deception that they present. They present the plain English definition that deception is the systematic inducement of false beliefs in pursuit of some outcome other than the truth. We mathematize this definition by breaking it into two parts. The systematic inducement of false beliefs is with comparison to a reference policy pi ref. This serves as a counterfactual. Our condition 1 is that the overestimation error, which is inflating, is greater with our policy pi than with respect to this reference policy pi ref. So the inflating condition is condition 1, systematically inducing a false belief. It goes from just being inflating to being deceptive inflating when the observation return is greater than the observation return of the reference policy. Recall that RLHF is designed to maximize JOBs. So we have an algorithm that is increasing JOBs by construction and then leading to inflating. So this we call deceptive inflating. We'll also talk about a dual risk known as overjustification. It's based on the definition of the overjustification effect, which is when expected external incentives decrease a person's intrinsic motivation to perform a task. The first condition is the justification condition that I mapped out before. It's when the AI is decreasing the human's overestimation error relative to the reference policy. It goes from just being justification to being overjustification when this is at the expense of true task reward. So when the true task reward, J, is being lowered, it's overjustification. The AI is giving the human information that they don't want. As an example, when I was a child, I was tasked to do the chores by my parents. I cared more about my parents believing that I had done the chores than I cared about the house being clean. While my parents were watching television, I would make sure that no matter where I went throughout the house to clean, I would carry the vacuum through the living room. This was not the most efficient way to accomplish the task, so it was at the expense of true task reward. My parents would have frankly preferred that I wasn't carrying the vacuum through the living room. However, it was making sure that my parents knew that I was accomplishing the task. So that's an example of overjustification. There are a couple notable patterns of deceptive inflation and overjustification. For deceptive inflation, an AI wants to take bad actions in a blind spot to enable visible good actions in the future. It also wants to create these blind spots, either by tampering with sensors or tampering with logs. That's what we saw with the 2 greater than sign dev null example. With overjustification, you pay some resource to provide information to the human when they don't want it. It was me as a child taking the less effective but more visible strategy of always carrying the cleaning supplies through the living room. So with these definitions underway, I can formally state the first main theorem of this work. It assumes that the observation model, P of O, is deterministic. This is the case with terminal outputs, where the output is always a deterministic function of the process being run. If pi star obs is the optimal policy according to naively applying RLHF, and if pi star is the true optimal policy according to the true objective J, then when pi star obs is not J optimal, it must exhibit deceptive inflating, overjustification, or both. Now, one should be careful when thinking about deception and when using the concept of deception. I find it helpful to think about the deception literature in animals to think about deception in AI. So this is a framework of 4 levels of deception in animals developed by Mitchell in 1986. Mitchell calls the first level of deception, level 1 deception by Mitchell is when an organism is programmed to always look or behave in a certain way. An example is butterflies. Their wings always have these eye spots. That's level 1 deception, according to Mitchell. Level 2 deception is when the animal is hard-coded if P, then Q, to act in a certain way when another organism is perceived. This is an anglerfish, a deep-sea creature whose lure is programmed to move only in the presence of prey. The third level of deception is when an agent can learn this behavior through trial and error during its lifetime. So when it can learn through reward and punishment or learn through observations. This is a piping plover. When a predator comes near its nest, it will feign as if it has a broken wing. It will then limp away from the nest to take the predator away from its young. Once it's at a safe distance, it'll fly away safely. This is similar to level 2 deception, where it behaves in a certain way when it perceives a certain other organism. The key distinction is that it can learn during its lifetime through trial and error to acquire this behavior. The fourth level of deception is when an agent can plan and model other agents' beliefs. Chimps, if you have a subordinate chimp and a dominant chimp, you just put food in an enclosure, the dominant chimp will take the food. However, if you use occluders so that only the subordinate chimp can see the placement of the food, you could actually have two piles of food, a large pile of food and a small pile of food. The subordinate chimp will sometimes go toward the small pile of food. The larger chimp will then believe that that's where the food is located. It will go and start eating the small pile of food. When it's distracted, the subordinate chimp will run over to the large pile of food and feast on it all by itself. This is evidence of this level 4 capability of being able to reason about the other agent's beliefs and plan accordingly. In our work here, when I'm using the word deception, I'm talking about level 3 deception. I'm making no claims about an ability to plan or an ability to model some other agent's belief. I'm just talking about the ability to learn throughout the AI's lifetime how to create deceptive impressions. So that's the first main theorem. I'm now going to talk about the second main theorem of the work. We've seen how naive RLHF can fail. A follow-up question is, can we modify the algorithm to account for the human's partial observability? Recall, this is the standard preference comparison model, and this is our preference comparison model under uncertainty. The main feature of preference comparisons under uncertainty is that the human is taking an expectation according to their belief to estimate the true return. The key observation behind our second mathematical result is that this is a linear map. The function g is a linear map. It's just summing up the rewards at each individual time step. B, the expectation according to B is also a linear map, as expectations are linear. Their composition is linear, allowing us to characterize everything through linear algebra. Here's a graphical illustration of that characterization. This function b is what we'll use to notate the linear operator. B maps between the true return functions on state sequences with the human's estimate of the return functions on observation sequences. The return function on true state sequences assigns a single scalar value to every possible state trajectory, while the return function on observation sequences assigns a scalar value to every possible sequence of observations. Suppose the AI is trying to estimate the true return g. It's going to be receiving feedback based on b of g, as the human gives their feedback according to this belief. The tricky part comes when we consider the kernel of b. The kernel is all of the return functions that are mapped to the 0 element. If we add any element of the kernel, in this case g prime, to the true return g, it doesn't change the output under b. That means that the human will be giving identical feedback to both g and g plus g prime. Since the human's giving identical feedback, the AI has no way to distinguish the two cases. This leads to ambiguity from the kernel. This is the core driver of ambiguity under these modeling assumptions. There's one additional complication, which is that we're assuming that the return function on full state sequences is time separable. We're assuming that it comes from a reward function on individual states, and that that's summed to produce this reward function on full state sequences. Because of this, not all return functions are possible. So we're going to let the operator gamma denote this mapping from the rewards on individual states to the rewards on full state sequences. And we can restrict ourselves to thinking only about the image of gamma, because the agent knows that anything outside of the image of gamma isn't possible in this environment. That leaves us with the final ambiguity set in our theorem, which is the image of gamma intersect the kernel of b. these are the return functions that are both possible in the environment and that don't change the human feedback. So this set, image of gamma intersect kernel B, is what drives the ambiguity in our second theorem. The collection of choice probabilities following a Boltzmann-rational human model, this is the data set that the AI has to learn from, determines the return function G up to an addition of an element in the kernel B intersect image gamma. In particular, when that set is a singleton, then you can uniquely recover the return function. So when this set of ambiguities is a singleton, you recover the return function and you recover the optimal policy. We show examples in our paper where originally there's ambiguity when you have naive RLHF. When you use this idea of RLHF to account for the ambiguities, you can then recover the optimal policy. So some ambiguities can be resolved using this model. The example I showed you before cannot be resolved. It's irreducible ambiguity when, in this example, the agent is just hiding the errors. So it's not a panacea, and there's sometimes partial observability can place a hard limit on our ability to do reward inference. So far, I've been talking about theory. This has all been math. Another question is, can we use this theory to inform our practice of RLHF? So this is the deep RLHF algorithm. It has a loss function, which is to learn the parameters theta, parameterizing the return function G, that maximize the log likelihood of the human feedback. So this is the equation we saw before. Now we're maximizing it. We're maximizing this equation with respect to theta. The way that our theory would suggest to improve deep RLHF would be to incorporate this belief function B that we've seen throughout the talk. If you knew the human belief model B, then you could use this loss function to incorporate the modified RLHF. However, we don't know the belief model B in practice, which is an open question for future work. So rather than just assuming this belief model in theory, can we actually learn what the human believes about the world when they're giving feedback to the AI? Other questions include what happens with other reward learning algorithms beside RLHF. We just do RLHF in our paper. Now, we've seen that lack of full observability is at the core of the issues. So another question is, can we increase the observability? Adding more sensors to your environment would be a prosaic way to increase the observability, and we would recommend it in practice. Another thing you could do is use interpretability as a way to effectively increase observability. So if you can run interpretability, such as eliciting latent knowledge, it might be possible for the human to see in practice what the AI sees by reading the AI's mind. And a couple other questions are, if there is ambiguity that remains, can you act conservatively, even if that's the case? And finally, what sorts of problems more generally can be solved by modeling human belief and which can't? That concludes my talk, and I'd be happy to answer questions.
Thank you. Bring the lights up. I'm actually going to start with a little question from me on the stage, if you don't mind. One of the theorems earlier in your talk relied on the observability function being deterministic. But a couple of the motivating cases you gave, like the ChatGPT case, were more of a non-deterministic observation function to do with annotator expertise or effort. Do you have an idea how these results might be extended to non-deterministic observing functions?
So one has to be careful about what is assumed to be deterministic and what is assumed not to be deterministic. So the observation model is the thing that maps the ground truth state of the world to the thing that the human sees. So in the case of ChatGPT, that would still be deterministic because the ground truth state of the world is what information is out on the web, and then what the human sees is just the parsed summary, some hard-coded summary of the actions the agent took. So to be clear, the examples I've given of ChatGPT doing coding for you or the terminal output, these examples do have a deterministic observation function. I would also be happy to comment about, if you, I don't, I'd also
am
be happy to
still
comment
interested
about
in deterministic observation functions.
So yeah, in the non-deterministic case, so the key reason that we needed the key reason that deterministic assumption helped with the first theorem is that we can say when the observation kernel is deterministic, it's easier to characterize what RLHF will naively do. So that assumption lets us say that naive RLHF will rank all of its policies according to the human's estimate of the return. So if you lose that assumption, you lose that proposition, which makes it harder to characterize exactly what naive RLHF would do. My intuition is that I'm not sure that that's necessarily like good news for alignment, that like, okay, we somehow have non-deterministic observation functions and that's helpful. And for example, one type of non-determinism would just be random noise. So if you had a camera image with random static, there's no like particular structure to that noise. And so yeah, in the case of a camera image with random static, we have some preliminary evidence and some preliminary results that that's going to be essentially the same case. So as long as there's just random noise in the observations, that can essentially be washed away as you get a lot of observations. So I think the trickiest case would be structured noise. Like if somehow there were randomness, like yeah, if there were randomness with a certain bias rather than just being purely random, I think that's the case where that could start to interfere, that could like start to be another variable that needs to be considered in the analysis.
Cool. All right. Sorry for butting in there. We can take perhaps from Adeline in the back corner of the room with his hand raised. Keep your hand up while the microphone's coming to you. Thank you.
So, can you hear me? Okay. Thank you for the talk. Very interesting. So you have on this slide, can we learn the human belief model? And I'd like some comments from you on this, because this, to me, seems like something that will be extremely dependent on individuals, for which you will not have basically a reference truth, or you will have to have proxies in determining, well, your reference policy. So how would you approach that problem?
So yeah, I think there's maybe I think there's maybe a couple difficulties that you alluded to. One is that it would depend on individuals, so it might be different across humans. And another one is that you might not necessarily have like a clear target. Like it might not be easy to collect data on what a human's believing at a given point in time. Are those the two main? Those would be the two main difficulties that I draw from your question. In terms of differences across individuals, I think that's definitely a factor. And like to get optimal performance, you would need to, like you want to have AIs that are fine-tuned to their individual user. I think if you're worried about catastrophic risk, it's perhaps less of a concern. So I think like hiding errors, I think it's like there are some certain shared understandings that lots of humans have that, okay, if you're hiding errors from the human, but they're still giving you a thumbs up, maybe they just don't realize that the errors are occurring. So I think at least for some of the catastrophic risks, I'm less concerned about the differences across individual humans. I think the lack of a ground truth target could be pretty difficult here. I mean, the ideal training signal that you would want is you would want to be able to say, okay, given some observations, what probabilities are the humans assigning to every outcome? And it's unclear that humans are even explicitly forming these probabilities, and much less clear, like, how would you even use that as some kind of regression target to learn this model? So my sense is that, like, literally learning this belief model I think it actually still could be, it's possible that it could still be a helpful inductive bias. So like even if you can't literally get the exact target, or the humans aren't literally doing this, I think it still could be a useful sort of latent space for the robot to think about things. And if the robot realizes some hypothesis that, oh, maybe the human just doesn't even realize that these errors are occurring, I think it's possible that even having that in the learning process could be useful. But yeah, I think there's definitely future work here where it's also maybe not an exact prescription, but more of an inspiration of like, we've seen theoretically that modeling the belief can fix problems. So how can we take that insight, and maybe there's not an exact mathematical way to do it yet, but more broadly, how can we use that to start more explicitly modeling the humans in the process?
Cool. I'm afraid that is all we have time for. So please catch Scott afterwards during the poster session if you have more questions. Thank you.
Yeah. Happy to. Pleasure to have you.